lecture with Julie Kramer White. Today we're talking about putting human in human spaceflight. Julie Kramer demonstrated mechanical aptitude at a young age. She was the one who owned a treasure toolbox, the one who would fix a washer, the recliner, or whatever was broken. So when a strong academic talent in math and science became apparent to her middle school teachers, she was a natural recruit for efforts focused on bringing more girls into math and science during the 70s. Though engineering interested Julie, she knew she didn't want to just design machines. Instead, it was the challenge of human spaceflight that appealed to her, and she set her sights on NASA. At the age of 19, she arrived at Johnson Space Center in Houston, home of the engineers who designed Apollo and space shuttles. As a cooperative educational student, she began to learn what it took to fly humans in space. It became her career and her passion, and during 25 years working with the space shuttle, she learned a lot about engineering, spacecraft, and ultimately how NASA made human spaceflight look a lot easier than it actually was. She's currently serving as the director of the engineering directorate at Johnson Space Center, and we're very grateful to have her here today with us. So please help me welcome Julie Kramer White.
Why don't we start with a little video, she says. How do I make it go?
Space Station, NASA's Johnson Space Center serves as the iconic beginning to some of the greatest moments in American history. Moments that are triumphs of engineering and international cooperation. Today, we are leveraging our past successes to create even more daring missions from the moon. Made possible with the Orion and Gateway programs, which are both orchestrated out of Johnson, the desolate moon will serve as NASA's jump-off point as we journey to unlock the secrets of the universe and understand how it all began. Today, we push forward to the moon. Tomorrow, we leap to greater heights and new destinations. There is history to be made. In Mission Control, we eagerly anticipate the first transmissions from unexplored worlds. Giant leaps start here.
So welcome. Thanks for having me here tonight. It's great to be here to talk about NASA JSC on Rice campus, and of course you guys are going to be going to JSC to look around, I think a little bit later, maybe next week. So I'm going to talk a little bit about human spaceflight, past, present, and future. Talk a little bit about JSC, history, capabilities. I'm going to talk about including JSC engineering, which obviously is my home at the Johnson Space Center. So I'll talk a little bit about that, and hopefully I'll give you a broad context for an overview of all the human spaceflight programs that we're participating in at Johnson Space Center, and hopefully orient them a little bit for you in terms of the broader strategic goals that NASA has from an exploration program. So finally, my plan is to leave a good bit of time at the end for Q&A. It's actually my probably preferred part of this whole thing. So the goal of the presentation is just to kind of get everybody on the same footing, and we'll go from there. A little bit about myself. Appreciate the introduction. I've been at Johnson Space Center for 37 years. I started out as just a journeyman engineer, grew up doing structural mechanics, so structures, stress, materials. I went from there into systems engineering and supported the Space Shuttle orbiter for many years. I worked on the Columbia accident investigation when that occurred, and then after that, I went on to work at the NASA Engineering Safety Center, which was stood up after the Columbia accident. From there, I became the chief engineer for the Orion program. I actually stayed there for 11 years from contract award through its initial flight tests, EFT-1. And after that, I moved up to become a directorate manager in the engineering directorate. So really important time. That was right when Dragon was beginning to fly its first crewed space flights. And so I actually went to that directorate position to kind of help our teams and the SpaceX teams make it through that process of human certification. I've been director now. I'm going into my 4th year as director. Quick survey across NASA. I'm sure most of you understand this, but just to understand JSC's role a little bit better, you know, NASA's composed of 10 field centers and many, many specialized test laboratories. 4 of those have been around since NACA So when you look at Langley and Ames and Armstrong and Lewis, which was Lewis, now is Glenn, those all started as aeronautics facilities having very widespread wind tunnel capabilities and engine test capabilities. Obviously, since the days of NACA, they've diversified, and most of them do human spaceflight or R&D for human spaceflight missions as well as science. But they go way back into the aero part of the agency. Marshall Space Flight Center, obviously most famous for development of the Saturn V, and now for SLS and the human lander systems that are being developed in the agency. Kennedy Space Center in Florida, which is where all the launch complexes are. JPL out in California, really operated by Caltech, so a little bit different in terms of NASA centers, but does a lot of robotics and interplanetary missions as well as deep space network activities. Goddard Space Flight Center up on the East Coast is tasked with increasing our knowledge through Earth observation and solar system observation. Obviously, programs that have a lot of visibility like Hubble Space Telescope and James Webb Space Telescope come out of Goddard. Johnson, though, was originally the Manned Spacecraft Center and really created in 1961 on land donated by Rice University, so a long-standing relationship between JSC and Rice, was tasked specifically with coordinating and implementing NASA's human spaceflight objectives. Renamed in 1973 after Lyndon Johnson, the 1,600-acre campus has satellite facilities north of NASA at Ellington Field. I think you guys will get to see the NBL. So that's up in that area, the Sonny Carter Training Facility, as well as our aircraft are all housed up at Ellington Field, the aircraft that are used for training the astronauts. We also have a hazardous testing facility out in Las Cruces, New Mexico, where we do a lot of heavier propulsion testing, as well as oxygen flammability testing. So while I think that most people realize astronauts and mission control are located at JSC, I think within the confines of the main campus, there are really a lot of things that support human spaceflight, a lot of facilities and capabilities, many uniquely developed for human spaceflight. We have operations facilities like the Modern Mission Control Center. We have training facilities. You'll see the SVMF, the Space Vehicle Mock-up Facility, which is a large, full-scale facility where we train folks for ISS, Soyuz, Orion, have mock-ups of all the full-scale vehicles there for crew training. They have the Neutral Buoyancy Lab. We have a gravity offload system, which allows us to train our astronauts in artificial gravity simulation. We have a lot of unique engineering facilities for spacecraft-sized testing, including spacecraft-sized thermal vac chambers, spacecraft-sized anechoic chambers. So these are very large-scale chambers that were built for human spacecraft back in the 60s. They're maintained today and still active. The engineering and science laboratories, we have testing of materials, avionics, pyrotechnics, as well as sophisticated simulation capabilities on site. We have research facilities for biomedical research, as well as astromaterials. All the curatorial samples, basically everything that did not exist on the planet Earth when it started, is stored in the astromaterials vaults at JSC. We have a lot of spaceflight analog facilities. Some of you may follow CHAPEA, which is our year-long Mars habitat, which is going to open up on July 6th. So the crew has been in there, a crew of 4 has been in that facility for a year, simulating life in a Martian habitat. So these facilities are obviously occupied by a lot of engineers, scientists, project and program managers, and mission support personnel, all kinds of engineers, aero, mechanical, EE, computer engineers, maybe less obvious, but also prevalent, chemical engineers, industrial engineers, biomedical engineers. We have all kinds of mission support people. We have procurement, business, HR, facilities, IT. It's like a little mini city, and that, all that infrastructure is there to support our human spaceflight programs. 3,000 civil servants, almost 11,000 people total when you count the immediate contractor community, really kind of creating a little ecosystem that supports our human spaceflight programs as well as our partners' human spaceflight programs. Since I have the stage, I do want to talk for just a few minutes about engineering. Sometimes we're hidden, perhaps a little bit more behind some of the sexier things that they do at the Johnson Space Center, but being an engineer and of course being director of engineering directorate, I feel like engineering is really the foundation of everything we do in human spaceflight and what it takes for NASA to accomplish. So within the engineering directorate, it's our job to support the design and development of all human spacecraft and human exploration systems, certainly within the United States, but we also participate a lot with our international partners in assisting them in their human spaceflight goals. We train up our people to support critical domain expertise, whether it's human spacecraft systems or systems integration. We do conceptual architecture work as well as mission analysis and planning. And we do technology development. A lot of it's relatively high TRL. It fits kind of the immediate requirements of the human spaceflight programs. If there's a problem that they need solved, we tend to go around the agency, pick up lower TRL technology, and field it to support the objectives of the human spaceflight programs. So we take that knowledge and we apply it to sustaining existing human spacecraft, like International Space Station, as well as designing the next human spacecraft. So I have engineers of 800 engineers, 2,000 contractors that support engineering. I have engineers deployed into all the human spaceflight programs. But we also do a lot of our own work internal to the directorate. So we do a lot of design, development, test, and evaluation of spaceflight hardware for things like the Exploration XEMU, so it's the new generation spacesuit upon which the Axiom suit is designed on that design reference. First spacesuit designed in over 40 years. We did the high definition cameras for the XEMU on the EMU on space station. So if you've seen really nice high def video coming off a space station, that's from cameras that were designed in our engineering directorate. We recently also built a lunar terrain vehicle ground test unit. So it's used in conjunction with our services contracts for lunar terrain vehicle to do risk reduction and test concept design to help them mitigate risk for their programs. And we just recently finished building Viper, which is the Volatiles Investigating Polar Rover. It's a little bit of an unusual project for us because our customer in this case is not actually human spaceflight, it's the Science Mission Directorate. This rover is in vibration testing now and is to be delivered to the South Pole to do investigation via the Commercial Lunar Payload Services contract. We also have a lot of very big complex test facilities on site. We do space environments, as I mentioned, largest thermal vac chamber, a human-rated thermal vac chamber, right? So not just the spacecraft, but the people in the spacecraft and the spacesuits can go into our thermal chambers. We have specially trained crews to do that. We do a lot of inflatable burst testing out on our hazardous part of the facility on the north side of the facility. We did parachute drop testing for all 3 human-rated capsules that are in service right now, as well as we do all the docking performance testing for all the vehicles that come to space station now. All their certification is done by test and analysis supported by Johnson Space Center. A big part of NASA's responsibility is not just to kind of understand some of the challenges we have in space, but to produce tools and simulations that they can then share with industry and with our partners to help make their jobs easier. So NASA does have a long history of developing various analysis tools. If you're familiar with NASGRO, was developed at Johnson Space Center. Engineers that developed it, one of the most famous ones, a guy named Royce Foreman, recently retired out of Johnson. But we also developed tools like Copernicus, which is sort of the industry standard for a lot of trajectory mission design work. We do a lot of transport analysis, and we also do a lot of simulation, either virtual reality simulation or augmented reality simulation, which you can imagine for space station being able to train astronauts via augmented reality is a big help. So I want to take a bit of time to talk history of human spaceflight before I launch into future. So looking at this chart, looking at the last 60 years, actually the first thing I thought about was that my career spans almost half of this chart, and so it actually made me feel pretty old looking at the chart. But the second thing I thought about, after I thought I was old, the second thing I thought about was really kind of looking at the difference between when these vehicles were conceived and when we started the conceptual design of them and when they were actually fielded. You know, shuttle was a gleam in somebody's eye in the 60s and really went into earnest design and development in the 70s and was fielded in the 80s. International Space Station, I can remember, was under development when I started in the mid-80s and was permanently manned in the year 2000. So it is a long process to develop some of these human-rated spacecraft. The more complicated the mission requirements are, the longer the development cycle tends to be. Finally, the other thing I thought about was this massive leap in kind of mass to orbit, right? You look at Mercury and Gemini compared to the tonnage that we had to put up for space station, and some of the designs we see now for human lander systems, the amount of tonnage that we are able to put into orbit is amazing and really no comparison to what we were doing 60 years ago. So JSC has led all these programs through a lot of really great moments in human spaceflight history. So whether it's the Historic Mission Control Center, which I think you'll get to see Mission Control while you're at JSC. I hope you'll get to see the historic one, ashtrays and cigarette butts and all. It's actually it's a pretty amazing replica, very painstakingly historically restored of what it was like to work in Mission Control in the 60s. So whether it was historic firsts like walking on the moon or spectacular saves like Apollo 13, JSC is really committed to stewarding and sustaining these multi-decadal human spaceflight programs, whether it's shuttle or station. It's really about not just sustaining the programs, but the people and the skills and the facilities that it requires to keep these programs continuing to fly safely. So as we've discussed, JSC houses a lot of unique capabilities and facilities that support not just our human spaceflight programs, but our partners' human spaceflight programs as well, whether that be international partners or whether it be industry. So what do we think we'll see in the next 60 years of human spaceflight? So in the next 60 years of human spaceflight, we certainly will eventually see the retirement of ISS. So you'll see ISS bridges both of these, both important historically because of what it represented in terms of the mammoth engineering accomplishment that it was, but also what it represented from an international partnership perspective. But it also bridges a lot of important objectives we have in the future. It eventually will be replaced by commercial destinations. We'll see a lot of NASA astronauts, as well as others, hopefully lots of others, traveling to commercial space stations in low Earth orbit. We'll see Orion continuing to venture into the cislunar space area, supporting both lunar surface and gateway operations, and all the while we'll be working towards a sustained presence on the surface of the moon. Front and center in the image is going to be cislunar space, certainly in the next several years or decade. That'll be where the focus will be, is to put down that permanent presence on the lunar surface. It's an important analog for a lot of reasons, right? If you can't live and work and stay on the moon, it's really hard to imagine living and working and staying on something like Mars, right? If you can't manage 3 days and 200,000 miles from home, you're really going to struggle, 8 months and 30 million miles from home. So none of this is going to happen, clearly, without a plan. So let's talk a little bit about the plan. First thing I want to talk about is low Earth orbit. A lot of the things that are happening in low Earth orbit are not random, right? JSC has been on a plan, NASA has been on a plan for a long time. It's basically a 5-point plan for the commercialization of low Earth orbit. First of those foundational elements is commercial activities on space station, right? Using space station to help demonstrate the value of micro-G science and to build a customer base. So you have to have somebody that wants to do business in low Earth orbit to build a commercial economy in low Earth orbit. So ISS is acting as a bridge for many of those activities, and we'll talk a little bit more about those. NASA is supporting private astronaut missions, right? Getting commercial companies that are interested in flying commercial missions to space station, not just NASA missions, and they pay for that privilege. We work on commercial LEO destinations to eventually replace space station and give people a place to go other than International Space Station. We continue to actively seek out industry, kind of what do they need to remove barriers and enable a commercial economy in low Earth orbit. We actively work that part of the process. And then a big part of it as well is what is NASA's long-term demand for low Earth orbit access, because that will help set the foundation for some of the financial concerns that the companies have, right? You can't have a company if you don't make money doing it ultimately. So what NASA does as a partial tenant is an important part of the process. So kind of ticking through that plan, part one, International Space Station, permanently occupied since November of 2000. It's really kind of the old man of the human spaceflight program, right? We spent a lot of time doing maintenance. It's a trooper. We don't have a whole lot of problems with it, but it is real that it takes a lot of maintenance to keep space station working. ISS has evolved. It's evolved, again, from this sort of demonstration of complex space construction and international partnership into really a cornerstone of commercial LEO development. So it's also a platform that we use for developing advanced technology for both lunar exploration and Mars. So if we're going to be using it on the lunar surface and it's new technology, we do everything we can to try to demonstrate it on ISS. Things like the life support systems and the regenerative life support systems have been tried on space station just to get a feel for what the issues there are going to be. So ISS works in ISS National Lab, which has put increased emphasis on utilization, science and commercial utilization on space station. So we host small businesses, entrepreneurs, researchers to test science and do technology in space. A big part of what ISS manages and monitors is, are we doing a lot of utilization on space station, not just maintenance, for example. We buy our ISS cargo. ISS cargo is all supplied essentially by 4 vehicles. 2 of those are commercial. So Dragon flies to us and brings cargo, as well as Cygnus. And 2 more commercial cargo vehicles are in development. So we just signed an agreement with ESA to develop a European cargo vehicle for space station. And I just had them in talking to me last week about opportunities for partnership on that. And Sierra Space is wanting to bring a winged vehicle back to space station, which as a shuttle person, I find the idea of seeing a winged vehicle back at space station pretty attractive. We also pay for crew rotation. That crew rotation now is mostly done by SpaceX with Dragon, but as many of you I'm sure are all aware, you'd be living under a rock, right, if you didn't know that the Starliner guys are up on space station right now as well. I'm sure that will generate some questions. And I will do my best to answer them all. Some of them I just don't know the answer. Current complement of ISS, this is important, right, because we have not only Expedition 71 there, we have Starliner there. That means you have 9 crew. That means you get a lot more utilization done. These guys are up doing science and research every day, all day. These are the commercial vehicles, along with Progress from Russia and HTV from JAXA, that supply all the supplies to space station. SpaceX has been delivering cargo since about 2012. SpaceX Cargo Flight 30 just flew back from space station in April, and Northrop Grumman has been delivering cargo since about 2014. And Northrop Grumman 20 flew back earlier in the spring, and they're fixing to go again in August. So it's on a regular cadence between Dragon and Northrop Grumman. And it's actually working really well. SpaceX has been delivering crew to ISS since 2020. Is gearing up right now for Crew 9, which is slated to come in August. And Boeing just delivered their initial crew to ISS with CFT. So Starliner 1 is expected sometime in 2025. So part 2 on the plan is commercial astronauts, private astronaut missions, right? So this is Axiom 3, which is the 3rd private astronaut mission, including the first Turkish astronaut. So it's a pretty cool opportunity. We've done 3 of these so far, and we have a 4th one coming in the fall. And the plan is for space station to host these crews regularly, a couple times a year on space station. Part 3 of the plan, commercial LEO destinations. NASA actually has 3 active contracts related to commercial LEO destinations. Axiom starts as an element of the current space station and ultimately separates and becomes a free flyer at the end of life of station. But there are also 2 free flyer stations under development. Starlab, which is a partnership between Voyager and Airbus, obviously the European company, and Orbital Reef, which is Blue Origin and Sierra Space. So that's kind of what's going on in low Earth orbit. I think the plan towards commercial development is going pretty well. I would say we've talked about commercial development in LEO for many, many, many years, but I would say really until 5-10 years ago, it wasn't really viable, you know, and now at this point, you're kind of a little bit this tipping point. It's still pretty fledgling, but continuing to push it across that tipping point, we think it'll remain healthy. So we'll continue to work that. Obviously, we put a lot of energy into that low Earth orbit plan because we want low Earth orbit to be commercially successful so that we can turn more of our resources to exploration goals. So let's talk about exploration plans. I'm going to take a little bit of a detour here before we talk about the moon, because with any large, complex endeavor, as complicated as going back to the moon is, it's difficult to create a sustained and consistent support for that program. This is equally true with lunar exploration. So while it's an area that in the United States has traditionally gained really good support across the political spectrum, it still can be, they change their minds, right? You go from one party to the other, and they change direction, and even if they only slightly change direction, it can really perturbate plans and can make progress difficult, if not impossible. So with the strong emphasis on international collaboration and commercial partnership and investment, it's really required for space exploration that NASA kind of pick a plan and be able to stay with it, because people don't want to invest in it if it doesn't stay static. So we're really working on underpinning our exploration goals and architectures and to give some stability. Is that my mic doing that? I thought that was in the back being super rude. They were like dragging around their chair in the back. Okay, sorry about that. You should have just been like, Julie, you're making noises, stop. All right, so in the process of trying to gain this stakeholder support, the agency has actually spent quite a bit of energy kind of going all the way back, right? When you're trying to get stakeholder buy-in, you really got to go all the way back to kind of the why go, right? And so recognizing that the value has multiple dimensions, whether that's science or inspiration or national posture, those are all very real, but NASA's exploration goals attempt to kind of scratch all those itches and balance those things out as we look and we define our objectives. So creating a sustained blueprint for a sustained human presence and exploration throughout the solar system, building on a foundational value of why. Then we use a systems engineering approach kind of to architect from the right, identify what it is we want to do, and we say basically, know your goal up front, create an integrated plan to achieve it. That sounds really simple. It can be extremely complicated in a highly volatile political environment, but with the help of the international partners and commercial industry, it's a lot easier. So as soon as international partners are committed to the plan, as soon as commercial companies are committed to the plan, it becomes easier to hold those objectives. So we take the top level goals and objectives, we drive the architecture. This is done in collaboration, like I said, with other government agencies, international partners, commercial partners, and academia. And the goal of this very detailed, and quite frankly to an engineer like myself, somewhat painful process is to get everybody on the same page about what are we trying to do. And are we all pulling kind of the same direction so that everybody understands their role and our partners have very clear objectives with NASA. We have a framework that we can stick to that allows people to have consistency of strategy, consistency of effort, consistency of purpose, which is particularly important for our international and commercial partners that need to get commitments, financial commitments. So it's really important that we hold that framework. So why I'm telling you this is I think it helps to understand kind of what's going on in the background. What's actively going on in the background is establishing these pieces so that the pieces of the moon campaign make sense. We wind up deriving a set of segments, whether it's human lunar return or foundational exploration or sustained lunar evolution or humans to Mars, goes from sort of building block approach, simpler to more complicated, phased over time, but that allows us to define what's required to meet those objectives, right? What elements do I need? What capabilities do I need? What systems do I need? What kind of operations capabilities do I need? That then allows international partners and commercial partners and NASA to kind of weigh in on, this is the part I would like to contribute, right? This is where my skills lie, or this is where I would like to grow capability. And so that whole process goes and starts assigning capabilities and roles and phasing to these different elements, which allows people to see kind of what their place is in this framework. We've talked a lot about international partnerships. Besides the significant effort to architect from the right and be clear about what our objectives and framework are, I think Artemis from the very beginning lays out a framework for collaborating with nations as we enter into this new phase of lunar exploration. I think the goal is to be able to share common principles, guidelines, best practices. It's really in many ways a reaffirmation of the Outer Space Treaty from 1967. Governs orbit, lunar surface, lunar subsurface, Mars, comets, asteroids, Lagrange points, kind of everything in between and all the transfer orbits that go between all those destinations. As of 2024, there were 43 signatures on the Artemis Accords. Obviously, not all of these countries are capable of sending big elements. But I think there is a commitment on everybody's part to say that each country should contribute as they're able. So we'll see astronauts from many of these countries. We'll see smaller contributions. We'll see new entrants that are learning to develop human spaceflight capability, and NASA and the other partners are committed to assisting in that endeavor. So let's talk about the moon. Let's talk about Artemis. So how are we doing against the exploration plan? Well, we spent the last 60 years talking about going up and down and the transportation problem, building bigger, building more reliable rockets, more up mass. We spent the last 40 years in low Earth orbit, learning to live and work in space for extended periods of time, and really watching for signs that commercial LEO as an economy is ready to take off on its own. And I think we really feel like that is viable now, and it's the right time. So then our first step becomes human lunar return, so the Artemis program. I'm sure you've heard the expression flags and footprints, right? More than flags and footprints, it's intended to be It's intended to provide capabilities, systems, and operations to sustain our presence on the surface for a long time and really reestablish that human presence and provide initial utilization around the moon. The architecture efforts we've discussed set in the framework for Artemis, it's not just a transportation system. So these are the elements as they're defined today. There's obviously more elements beyond this, but this is a revitalized ground communication system. I mean, the ground communication system around the world is aged, right? It was laid in the 60s. It involves landers, which we haven't had one in a long time. It involves suits, which we talked about the fact the suit we haven't built a new suit in 40 years. It involves the ability to build a base camp, which was never really an objective that Apollo achieved. It involves mature long-term space operations and Earth independence, as well as gateway, so a platform in a high orbit, near rectilinear halo orbit that sort of watches over all of it and acts as a gateway both to the lunar surface and onto Mars, ultimately for large-scale space construction. As you can see from this chart, international cooperation is built into the foundations of Artemis. ESA is involved with Orion. They provide the service module for Orion. They do refueling and a habitation module for Gateway. JAXA is committed to partner with ESA on the ECLSS, the Environmental Control Life Support Systems, for that habitation module, as well as a rover for the lunar surface. CSA, building on their heritage, the Canadian Space Agency, building on their heritage with ISS, is committed to producing the arm for Gateway, the robotic arm. And UAE, United Arab Emirates, which is a newcomer, is providing the airlock to Gateway. So when we look at the pieces, that's a real rocket, right? So Artemis flew on the SLS Block 1. Same design will be used for Artemis 2 and 3. So we have a rocket that has successfully completed its demonstration flight on Artemis 1. A larger upper stage is under development for Artemis 4 under what's called the Block 1B configuration. But essentially, so we have a big rocket. We have Orion, crew transportation. It's well on its way to Artemis 2. You can see actually Artemis 2 is in the foreground. Artemis 3 is on the left, and Artemis 4 is in the big white structure behind. So all three of those vehicles are in the manufacturing facility at Kennedy Space Center. And as a matter of fact, this is an older picture actually, because Artemis 2 now is stacked with the European service module and in the thermal vacuum chambers at Kennedy Space Center being tested under thermal vac conditions as we speak. The next piece would be the suits, the EVA suits. So the EVA suits, they're like a mini spacecraft, right? They have all the same kinds of requirements. They have to hold pressure, they have to hold atmosphere, environmental control, communication, human factors. It takes a highly integrated, multidisciplined team of engineers to create and optimize a spacesuit. The new lunar surface suits were being provided by Axiom and Collins. Ha 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 ha. So everybody read the news. It's not funny if you're Collins, but anyway, very recently you may have seen in the news that Collins was stopping development of their lunar suit, right? And I think the tagline remains the same, right? Space is hard. And these services contracts require not only that these companies do complex aerospace system development, but it's not just the technical challenge, they have to have significant corporate investment. They have to deal with the supply chain, which is bad right now. It is very hard to build space-grade hardware with the supply chain the way it is in the country right now. And now we're dumping a whole lot of stuff on top of it to be built. So it's very hard to keep up with demand. So space is hard. Building spacesuits is hard. New lunar suit development is definitely promising to provide much more capability than the Apollo suits have. If you're students of history, you'll know that the Apollo suits were difficult to use. The astronauts, if you fell down, you've seen the videos where they sort of bounce on the surface and struggle to get up like a turtle, right? That was a real thing. Lots of injuries of fingertips and toes, and in this case, we'll be going to the South Pole, in which the environmental conditions are even much more dramatic than the equator. So these suits have much better mobility, much better thermal and environmental control than the Apollo suits did. This situation presents I didn't know what to do with this chart. I actually had written this chart before the Collins thing happened. So I was like, on hold. We'll just call that on hold. And so it presents an interesting challenge for NASA because these commercial contracts, a big part of this is designed inherently to drive competition. That's why 2 vendors were chosen. So now NASA has to decide what gives NASA the best chance at fielding this technical capability when they need it, right? So will we either on-ramp another vendor? Will we continue in-house development? XEMU was at a pretty high level of development when it was paused to push the designs out to the commercial companies. So the program, those conversations are ongoing, and we'll have to decide as an agency, do we add a competitor to this process, or do we let it just ride? So those are all the kind of things you have to decide when we have this kind of development process. You don't get to the moon without a lander. Obviously, similar to suits, we have 2 concurrent services contracts for Artemis 3 and Artemis 5. Starship's making rapid progress on engines and structural system development. Blue Origin is slated to do a development lander flight on the Mark 1 later this year, so we'll get our first real look at capability. We've seen labs and things like that, but first integrated vehicle capability hopefully later this year. But both systems are very large, use a lot of propellant, have to do a lot of cryofluid management, so nobody has taken an easy route here. So this is going to be a challenge no matter who does it. It's a very big challenge. We also add to that surface mobility. Comes in 2 flavors, LTVs like the old lunar car, right? It's open, pressurized, unpressurized. We have 3 contracts out to do the initial year of development, and from that we hope to down select a lunar terrain vehicle provider. Again, competition is an important part of that process. Pressurized rover, as I mentioned already, will come as an international contribution from JAXA. So pretty excited about that. But you can imagine now I've talked about launch vehicle, human transportation, landers, suits, 2 types of rovers. So you've got a lot going on the surface, right? It's going to get really complicated really fast. So interoperability becomes an important attribute of what we're trying to do. And interestingly enough, we've let a lot of services contracts without a lot of interoperability requirements. So job security actually for JSC engineering, don't say that. So job security for me and my team, but it does present a lot of real challenges, right? You've got to be able to mechanically integrate on the surface of the moon. You've got to be able to pass power, pass data. So there's a lot of things that these vehicles and systems have to be able to do on the surface of the moon that makes interoperability a really important part of this process. I mean, imagine getting in a rental car and not knowing how to drive it, right? It has happened. I had to Google one time, YouTube, how to turn the car on. But the goal would be, right, that they can move from the spacecraft to the lander, to the rovers, and at least basically understand the caution and warning systems, understand the displays, and that can be really complicated when you're on services contracts. Gateway is going to offer a lot of extensive capabilities for sustained exploration and research in deep space as well. It acts as a stepping stone beyond the Earth-Moon system to Mars. It's situated in a really unique orbit. This near rectilinear halo orbit basically allows it always to be sun positive, always calm positive. So there's a lot of good things about the orbit it's in. We have 5 agencies already committed to building Gateway, as we mentioned, NASA, ESA, JAXA, CSA, and Mohammed bin Rashid Space Center, so that's United Arab Emirates. But it's significantly smaller than ISS. It weighs in at about 1/10 of the mass and about 1/3 of the habitable volume, so it's much smaller than Space Station. The initial Gateway contracts also already let and vehicles well under development, right? So the bus, the power and propulsion bus built by Maxar, and you can see these are the actual engines that are being tested for the bus, as well as the actual pressure vessel for HALO, which is the Habitation and Logistics outpost where the primary structure is being built by Tazi in Italy. And so it's already been built and it's in structural testing right now. So the idea obviously is you've let out a lot of contracts, you've got a lot of pieces in motion, and now you're trying to construct missions from these capabilities that are consistent with all these objectives that you've spent time establishing. Artemis 1, mission complete. Artemis 2, to send the face of exploration out and definitely test the environmental control life support aspects of the Orion capsule. Artemis 3 will be a big jump. As it's planned now, it's elements coming together in the near rectilinear halo orbit and delivering the crew to the surface. So that's a lot. That is a big jump from 2 to 3. We can talk about that too. Artemis 4 requires launch vehicle upgrades because it delivers more capability to Gateway. So imagine, flying more additional modules up to Gateway. Artemis 5, it starts putting down reusable infrastructure on the surface of the moon, things like rovers that are intended to be used for multiple missions. Artemis 6 delivers the airlock to Gateway and makes it sort of a fully functioning platform. Artemis 7 and beyond, you start dropping things like habitats onto the surface of the moon, and you start talking about infrastructure that's in place for sort of the long haul. So that will keep us busy for a while. For a while. But always the optimists, we want to be talking about Mars too, right? Because ultimately the goal is not to get stuck on the moon, right? The moon's a great objective as far as I'm concerned. It's going to allow us to learn a lot and develop a lot of capabilities, but that is not ultimately the objective. I mean, fundamentally, there's a lot of evidence that Mars was much wetter and warmer and had a thicker atmosphere, so a lot of obviously reasons why people from Earth might be interested in what happened on Mars years ago, and the best way to figure some of that out is to go. It's our nearest habitable planetary neighbor. It's got a lot of natural resources, oxygen, water, iron, sunlight that fuel things like in-situ resource utilization, which we haven't talked about a lot yet, but is a very important aspect of Mars. When you start, we will try a lot of these techniques out on the moon because they will allow us to develop capabilities, commodities, and consumables on the surface of the moon. But it really becomes necessary when you talk about something like Mars. So what we do on the moon ultimately is important to that longer-term ultimate goal of Mars, learning to live away from the Earth, deep space aggregation of spacecraft systems, suit development, managing dust. Dust is a problem on both planetary surfaces. Operations, both ground to surface and from orbit to the surface. But there are several unique challenges that are unique to Mars, and so we work on those already, right? So recognizing the moon won't solve the problem of interplanetary propulsion systems, right? We'll go to the moon on chemical propulsion. So it's close enough that the payoff isn't worth it. But when you start talking Mars and further out, the agency has reinvigorated a lot of things around nuclear electric propulsion, nuclear thermal propulsion. Solar electric propulsion, as I mentioned already, is being used on Gateway to position the modules and pre-positioning large amounts of supplies where they can go slowly. They don't have to go fast if they don't have the people with them. But virtually all the architectures for Mars pre-position significant supplies because of the mass and transit time challenges. So interplanetary propulsion systems is something the agency is actively working on with other interagency partners. Moon doesn't have an atmosphere, but entering and descending and landing on Mars with a very heavy human spacecraft as opposed to a robotic spacecraft is a big challenge. You can see here the scale difference between landing something like Perseverance and landing a human-class lander on the surface of the moon is a very different problem. And you have a very relatively thin atmosphere. So the technology to enable that, such as inflatable aeroshells, is under active research and development in the agency. As a matter of fact, LOFTED, which is low Earth orbit flight test of an inflatable decelerator, recently flew. It's a flight test out of Langley and re-entered the largest aeroshell to ever enter Earth's atmosphere. It's 20 feet, came in at 18,000 miles per hour, down to 80 miles per hour before it was recovered at sea. Orion is only 16 feet. So LOFTED is actually bigger than Orion is. So it's a pretty impressive accomplishment. Living and working on Mars presents a lot of its own challenges in ways that are different than the moon around terrain hazards, planetary protection, right? Obviously the moon's a sterile environment. Mars is a bigger problem. We'd rather not leave our cooties there, and we'd rather not bring their cooties here. And especially if we're trying to figure out what is native too, right? We gotta be really careful and not contaminate that. We have a 44-minute round-trip comm delay to Mars. The comm delay to the moon is virtually, it sounds like a little bit like you have a little bit of a delay, a couple seconds at most. You almost don't even notice it. Dust storms are of a totally different magnitude. So weather, right? You have to deal with weather on Mars, which you don't have to deal with on the moon. So a lot of really unique kind of attributes associated with the Mars problem that we aren't kicking those down the road. We're trying to deal with those in a technology development fashion now while we work the architecture pieces on the moon. So hopefully this has helped a little bit understand some of the context of why we're developing what we're developing, when we're developing it, and the unique role maybe that JSC plays with these programs, both technically and from a leadership perspective, starting with the commercialization of LEO, development of systems for sustained lunar presence, and working on the technology that's uniquely required to move on to Mars. And just so we don't think that all this is just PowerPoint charts, I will leave you.
Our return to the moon will be different than the last time. We plan to explore more of the lunar surface and learn how to
system
live.
is now counting down to liftoff of Orion on its maiden voyage to the moon. And here we go. Hydrogen burn-off igniters initiate. 7, 6, 5. 4-stage engine start. 3, 2, 1. Boosters in ignition. And liftoff of Artemis 1. We rise together back to the moon and beyond.
We are all part of something incredibly special, the first launch of Artemis.
This view of Earth from a human-rated spacecraft not seen since 1972 during the final Apollo missions.
Distant retrograde orbit. We're going to be about 38,000 miles away from the lunar surface. We're going beyond anywhere we ever went for Apollo.
The Orion spacecraft is barreling its way back home after circumnavigating the moon and beyond in an elliptical distant retrograde orbit. Splashdown. Orion, back on Earth.
My family is really tired of hearing that video playing from my office. I play it a lot. So when you spend, 11 years of your career developing a spacecraft, there's honestly, for those of you that have done it, you can appreciate it. For those of you that haven't, there is no experience at all, like taking something from a concept through requirements development, watching it test, watching it not quite do maybe some of the things it's supposed to do, rebuilding and getting it off on a flight test that, true to actually what you see in the press, was a pretty damn good flight test. So I'm pretty proud of that vehicle and our ability to build a rocket that damn big and get it off the launch pad the first time and not have a problem. So actually pretty proud of that team. So I am happy to field any and all questions you guys may have. I will do my best to answer any questions you have. So I appreciate your attention and have at it.
Hi, my name's Aman. I'm from the UK. I've got a bit of a minor question, and I think I'm at risk of slightly offending you.
I'm pretty hard to offend, honestly, so go for it.
Okay. Space Launch System is a pretty boring name, especially in comparison to like Saturn V, Falcon. What are the thoughts on that?
I'm not trying to be funny. I honestly didn't hear the beginning of your question.
Oh, sure. So I said the Space Launch System is a pretty boring name, especially in comparison to Falcon and Saturn V.
Right.
Yeah.
The original instantiation was Ares. Now that's a name for a rocket, right? Luckily, Orion was allowed to keep its name when you may follow American politics, and if you're space people, right? Constellation got canceled in 2010. Orion was able to emerge with Orion as a name still intact, thank God, because I had shirts that said Orion on it. I really didn't want to buy new ones. But But SLS did not emerge, even though, interestingly enough, it is virtually the same architecture. So if you go back and study the Ares architecture, there are a lot of aspects of it that are very, very similar to SLS. It's, in a lot of ways, a political thing. But yes, Space Launch System, not a sexy name, but it's still a sexy rocket. So.
Thank you.
Not offended. Now, if you'd have picked on Orion, we might have had a rumble. So.
Hi, thank you for the lecture, and it's very refreshing to see a woman in such a role. Congratulations.
Woo-hoo!
My question is about Mars. I saw we want to send humans on Mars. Everyone knows about Elon Musk, Occupy Mars, but it's very expensive to send humans there. We are the highest resource conditioned by our biology, and it's an expensive program. How is NASA thinking, and what are today ongoing in the agency concerning robots, AI, machinery, automated 3D automated techniques? So then we cut down cost, but then we also arrive in our lifetime there. Thank you.
That's actually that's a great question, and as a human spaceflight person, right, sometimes I struggle a little bit to answer that, but I do think there is an answer for it. The agency certainly is very committed to robotic exploration, right? There is a lot of enthusiasm around the work done by JPL, for example, Pathfinder and the Mars exploration vehicles, the Mars sample return missions. There's certainly momentum building within the agency on robotics and AI, but I will tell you, even as the person who those domains live under engineering to a great degree at Johnson, they are not our strongest domains. I think it's really the development of AI and robotics and things has been driven more externally, and we collaborate a lot with externals, but we tend to solve very kind of niche issues versus you see a lot of people deploying robotics into manufacturing and some of these areas where the robotics makes the financial piece of it work, right, over the long haul. Whereas for us, that's not as much of the motivator, right, in that equation. So yes, clearly to send people to Mars, very expensive, ultimately will be very risky, take a long time. And I think you almost go back to kind of the foundational tenets of why we explore it all, right? It goes back to science. Well, yeah, I can do a lot of the science with robots, right, and rovers. Although I have plenty of scientists who argue they can do a lot if you put them on the ground, right? Field research, there's an art to that. It's very difficult to teach a robot. But I would argue it's inspiration. It's seeing people, it's seeing a female director of engineering, it's seeing people on Mars. That's the key to me. And that's what ultimately will make it worth the expense when we decide to do it. It'll be the ability to say we had this very audacious, large goal and did this thing that no one else had ever done. We will do it collectively. It's not something one nation will ever be able to afford to do. So we'll have to choose to do it collectively. And we will achieve, ultimately either fail or succeed in that endeavor together, right? And it has a lot of international influence as well as inspiration aspects to it that I think will ultimately drive us to do it regardless of what it costs.
Hi, Alejandro Garcia, originally Dominican Republic and also US citizen. Following that question, do you foresee NASA leading that expedition to Mars, like the human expedition? Or do you think like Elon Musk and SpaceX or maybe international coalition would go, considering especially it's so many years in the future and risky and as you said, political changes and so on. So I'm curious about your perspective of potential scenarios.
Ask me in 5 years. And I really say that only because I think what we're trying to do on the lunar surface is a test case, right? Can we really make that commitment to an international coalition, commit maybe 10 years, ask me in 10 years. Can we, through political cycles for us, right? That's a real thing. So through political cycles, can we remain stable? We actually did remain fairly stable through the last political cycle, which is actually pretty unusual for us. So a lot of cross-aisle, cross-party support for what NASA's trying to do, which is awesome. So I would say really kind of not trying to be silly, ask me in 5 or 10 years, because I think what we're able to achieve on the moon, if we're really able to integrate the international partners and the commercial partners in the way NASA would like to, I think we will be successful and we will be able to go to Mars, and it will probably be an international coalition. What role will NASA play? I mean, I would like to think NASA will always be showing leadership and trying to be out front in kind of dragging everybody along with us, right? We want to go do this. You guys want to go do this. Come on, you do. You want to go. But we definitely take a lot of our cues from the international partners, right? The international partner community was very strong about wanting to go to the moon. You know, there definitely have been phases in my recent history with NASA, right, since cancellation of Constellation, right? The U.S. has waffled about moon Mars. Do we really need to go to the moon? Really, there are a lot of us that think the moon is the right place from an engineering perspective, right? My perspective is an engineering perspective. I don't want to take the car across the country. I want to take the car around the block before I go across country, right? So for me, from an engineering perspective, that makes a lot of sense. But there's been at times where we thought, oh, we'll go straight to Mars. And I think to a great degree, consensus with the international community has driven us back to the moon, which from an engineering perspective, I think is the correct answer. So I think it's going well in that regard. Ask me in 5 or 10 years kind of how that looks. What will Elon Musk be doing 5 or 10 years from now? God only knows. Love the man, but holy cow. Okay. So Elon will be on Mars someday. I have no question in my mind whatsoever. That's where I'll stop. He will get there, you know, so one way or another.
Hi, my name is James Fettis from the CSIRO in Australia. Thank you so much for your time tonight. It's been a really fascinating lecture. I was really interested by your answer earlier about AI and autonomy not necessarily being a strong suit, particularly from a human spaceflight perspective. Some of us are working on a team project on Gateway, and we've seen that the requirements for Gateway include up to 3 years of uncrewed operations and 21 days of no contact with ground control. Clearly, some level of autonomy and robotics is going to be necessary for that, and the groundwork for that will be important for crewed missions to Mars as well. We already know that external robotics and vehicle systems management are baked into the Gateway architecture, but internal robotics are a fairly clear engineering challenge given the small internal volume. My question is, given...
I was like, this is a really long question.
Yeah, sorry.
But you're giving me a good time to formulate my answer. So
yeah. No, my question is, given that AI and autonomy may not be a strong suit from a JSC perspective, where are you looking for those solutions? Where do you think that those things will be solved?
So I'm going to give you a little bit of correction. I actually didn't say we're not good at autonomy, right? We actually are quite good at autonomy. We have a lot of autonomous spacecraft, not just JSC is good at autonomy, right? Goddard Space Flight Center is excellent at autonomy. They've built satellites and spacecraft for years that operate quite autonomously. And so we've partnered with a lot of different centers. Our friends at JPL have learned to operate on very significant delay, right, working with their spacecraft. So they've learned a lot about autonomy. So I would say we actually have a very robust technical community within the agency with regard to autonomy. Robotics, on the other hand, as you noticed, Gateway is absent. Robotics. Doesn't make any sense, right? For a vehicle that's going to be autonomous for 50 of the 52 weeks of the year. Who's going to change out filters? Who's going to, don't tell me there's not going to be any maintenance, because I've been to that dance before and that does not happen. So that's a lie. So who's going to do the maintenance? Who's going to do the science, right? We talk about there's science that can be done in those autonomous periods, utilization of that platform, that if you have the right robotics support, you can do that. And so I would say AI, I can barely spell, so let's put a pin in that one for a minute. Robotics, I would say we are collaborating with companies outside, Woodside in Australia, for example. That was really good. I can make that connection, wasn't it? As well as a lot of automotive companies in the U.S. we've done robotics with as well. And so I'd say we are advancing robotics. We do several technology robotics type projects within JSC specifically. A lot of it is aimed at, again, I said don't do a lot of low TRL stuff. I don't do a lot of low technical readiness level stuff. I tend to do more applied. So like what I have my robots doing is slogging luggage, right? So I don't have to have astronauts in EVA suits spending literally all their time on the lunar surface slogging logistics, because that's what the models will tell you will happen without the robots, right? So we spend a lot of time talking about that. How do I get payloads off the lander? How do I get things moved around? How do I get the logistics from the lander to the habitation module, get it in and out? So we do spend quite a bit of time with that, and it's actually a lot of it's done in collaboration with commercial companies trying to work the software and the autonomy pieces of it with commercial hardware. Because a lot of the commercial hardware is there. It's got to be space hardened. It's got to deal with dust. So it's got to have some wrappers put on it that we know how to do. But in collaboration with those folks, our robotics teams work a lot with them on that. And a lot of the things that we really work, like VSM is done, actually coded by JSC Engineering. Pretty proud of that. We're the prime on Gateway to do that work. And so obviously we do know a lot about vehicle system management and autonomous vehicle operations. It's the robotics that we struggle a little bit more with. The agency can't quite decide. God, I hope I don't get in trouble for this. The agency, I feel like, my guys that do this will tell you we struggle as an agency kind of understanding our place in some of the robotics initiatives, and they don't get a lot of support. So they do most of their work in collaboration with the other federal agencies, DOE and DOD. They do a lot with international partners and commercial partners. And so they work really hard. They hustle really hard to make those relationships outside the agency, because inside we're a little bit conflicted. We kind of don't know what to do, and they don't get as much support as they should have to be able to answer the questions that you're asking about Gateway. We are going to have to field robotic systems for Gateway. Gateway does not want to pay for them. Gateway is like, do not come to me, engineering, and tell me some pipe dream thing you got about robots you want to build. They don't want to hear it. They want me to go find robots or build robots, they don't really care, but they want me to show up at space station with robots and show them that my robots can do what they need me to do, and then they want to buy my robots, which does not help me at all. So we are actively having that conversation. What you will find in Gateway is some things like some scarred-in structure, infrastructure that would allow robots to be added. So like they know, they just can't stomach the bill right now. And so it's a dance we kind of do with them that we have to figure out. But a great area for commercial collaboration with our folks that can kind of translate some of those commercial capabilities, understand the robotics, definitely understand the autonomy, and can translate it to our applications. AI is more complicated. Man, if the agency's conflicted about robotics, they really are conflicted about AI. I mean, I think they're worried about, like, that everybody's gonna get our data, and like the AI thing is gonna come, and so that there's these very real security barriers around ITAR data and proprietary data from all our partners that's mixed in kind of with all of our data. So the agency is proceeding very cautiously with respect to AI, but I think a lot of the solutions we see will come from outside. Honestly, they will. We will be users. And so we will describe use cases where AI would be extremely helpful to us. And we are already doing that, right? Where we talk about, hey, if I had AI, this would be helpful to me in how I do my engineering job every day, improving the efficiency of my engineering teams, not even the space operations part of it, just the how I do engineering. So we work those use cases, but I honestly believe the solutions will come mostly from outside, because big data outside is just outpacing where we are.
Hello, I'm Francesca. Thank you for your time. And so I have a question about, because this morning some of us were involved in an orienteering workshop done by one of your colleagues who trains astronauts at NASA. And so it seemed like it's very important still now for astronauts to be able to read maps and navigate around, okay? So my question is how and in which step of this Artemis roadmap is envisaged to have some kind of telecommunication constellation around the moon, such that the astronaut can use GPS or GNSS similar services. And then a very short second question, maybe is something that I should know, but is the Orion capsule that comes down like in Artemis 2 the same that will be used for Artemis 3 or not? Okay, this is
so
just...
the capsule that comes back with 2.
Yeah, is it the same?
Now you're going to call me a liar because I've been away from the program for about 7 years now. But we will start reusing them. Eventually what they do is they start, one lands and then it has a period to be refurbished and the next one goes. You wind up with 3 of them that wind up rotating. So eventually they do go to reuse. I honestly cannot tell you. I can't remember for 2. Do they attempt to reuse right away? I think the answer is yes. I think they reuse the primary structure and some pieces and the avionics and pieces out of it. But then I just can't remember quite how they repackage it. But yes, it is going over to reuse. So it eventually would be not all reusable. You don't reuse the heat shield, right? You take off some of the pieces that are exposed to salt water. But the crew module, and if you can keep it dry inside the crew module, then yes, if you relatively calm seas, and you can recover it without getting salt water inside, then you're okay. So yes, we will use it. The other question, we really don't see many astronauts now that don't know how to navigate, kind of wilderness or survival type settings, because the next missions will require that they be able to navigate on the surface of the moon. The infrastructure related to communications, really, I think you'll start to, don't hold me exactly to the dates, I don't have the manifest memorized, but really it'll probably be like you see the LTV go down, the vehicles start going down on 5, that's when they really start moving around on you, right? Because up to that point, you're walking distance. You're in a suit. You're probably not going to get out of visual. I mean, if I'm going to the moon, I'm not getting out of line of sight with that lander, right? Even if it's a really big lander like Starship, you can only get so far from it. It's going to have a big beacon on the top of it. But so I think probably up to about 5, it's principally line of sight navigation. But once you start getting vehicles, you've got to have the telecommunication or surface communication laid in place to be able to go longer distances. So it goes about that time frame.
Thank you.
And by the way, there's some really interesting navigation studies of watching the astronauts try to navigate. I don't know what they told you this morning, but watch them try to navigate in a suit. Good job, bud. Good job.
Hi, I'm Sejal, and my question is, it's really fundamental. So the first question is, what inspired you to choose a career like space engineer? And the second question is, if you were to choose between applying your engineering principles for the betterment of life on Earth using space resources, or would you choose applying engineering principles for space exploration, and why?
So the first one, I was a byproduct of a push in the United States in the 1970s to try to get us to use the metric system and to try to get women to go to engineering school. We obviously failed on the metric system. We did better with getting women to go to engineering school. I was one of those kids that did really well in science and math, and my teachers told me, well, you should go be a doctor or an engineer. And I'm like, I'm not going to be a doctor, that's gross. So engineering appealed to me. It's fundamentally fixing things. I didn't have any engineers in my family, but fixing things appealed to me. Doing space stuff appealed to me, and so that was kind of the route I chose. And luckily, I really liked what I did choose. I've made my choice. My choice is to do exploration. I think the study of what is going on Earth is extremely important, and my friends at Goddard will be happy to help you out. But I've made my choice, and going and doing exploration is what I love. Not joking about that video, I watched that vehicle that I helped design go fly around the moon, and I think that's the freaking awesomest thing I've ever seen. So I'm ready to go.
Thank you.
Hi, Thea Russell from the UK here. Thanks for coming. It's awesome to have you. I just wanted to ask, the SLS is such a majestic engineering kind of feat. how do you see its kind of future with the moon missions when you've got projects like Starship kind of rapidly developing today? Thanks.
Yeah, good question. And a little bit crystal ball, right? Difficult to say. One of the things that I think is super important, I mean, we learned this, I feel like we learned this, we'll see if we can remember it very long, that having single ways of getting places is not an awesome position for us to be in, right? So I like multiple launch vehicles, I like multiple providers, I like different kinds of capability. I'll be very happy the day Starship lands on the moon. Until then, I've got a big rocket that can do a lot of stuff. It's expensive, I won't lie. I'm not gonna sit here and act like it's not expensive. It's expensive. It's an amazing piece of machinery. And the agency is attempting to reduce cost, right? I don't know if you follow like at the contract level, right? Orion has gone through a thing called OPOC, which is, again, my opinion, for what that's worth, which is not necessarily the agency opinion. The correct way to be doing contract development is cost plus, or something that motivates the contractor during the phases when you're making a lot of changes and you're still kind of figuring it out, and then you put them on a fixed price, and they build you copies, right? There's some exceptions to that, but, and Orion has gone through that process of, you know, committing to a certain number of vehicles through a certain kind of capability where they have a cost plus model, and OPOC transitions them, it's called Orion Production Operations Contract, transitions them to a firm fixed price contract at a lower cost per unit. So that's their cost will roll off after, I think, 5. They're on OPOC after 3, but I think their cost starts rolling off at 5, building copies. And then they start reusing copies, and the cost goes down. SLS is going through the same type of effort under a thing called EPOC. And don't ask me what the E stands for, but it's essentially, can we get a contractor to bid essentially building copies of SLS, and actually it encompasses ground systems as well. So you're buying, essentially now you're buying copies or buying a launch service. So I think the agency is trying to mitigate some of the costs associated with building that. But again, you know, the day that we are putting Starship down repeatedly on the surface of the moon, maybe SLS will become obsolete. That'd be awesome, right? But it's gonna be a long while before I wanna be dependent on a single source of getting people back and forth.
Hi there, I'm Adam from Northern Ireland. I have a little bit of a hypothetical for you. Oh, yeah, a wee bit louder. Yes, I have a wee bit of a hypothetical. Let's say Artemis is a great success and we've done all that we wanted to achieve on Mars in the later half of the century. Where do you think we should go next after that?
Ooh, that's a great question. And it's actually not my field of expertise, but I did see like a really awesome Smithsonian discussion of this just the other day, and talking about some of the moons around Saturn, which is pretty cool. So like, you know, Europa Clipper and some of these unmanned probes are going out now to study some of the moons around the gas giants, and understanding kind of what's possible in some of these areas where they still have liquid oceans underneath all the ice. So I imagine those will be kind of the next things we would try after we could demonstrate that we could live on Mars, and pretty cool stuff. I wish I knew more actually about it. I actually kind of was inspired by watching some of this discussion about the science of the moons and what they might be from an exploration perspective to learn a little bit more. So it's actually a pretty cool question, is what do you do with all that capability? Cool. That's so cool.
Hi there. Jeff from Canada, and on behalf of the 3 physicians, yes, it's often gross. I'm with the TP working on Gateway, and we talked to some of the engineers a couple days ago. We were talking about the fact that it's going to be shut down for essentially 11 months, at least for the first while. So there's interesting microbiology there and how that will get dealt with. You've mentioned changing of filters. What other engineering challenges come with that, and what thoughts are there in terms of what systems you do keep going versus what you don't?
Yeah, I'm sure. I mean, a lot of trades still ahead of us. The good news is a lot of the systems like the environmental control, life support systems, and power systems, now the state of the art, or I almost would call it a standard, is a regenerative system, right? Luckily, we're not. Certainly, we could use consumable systems, right, to go to the moon, and we could do it again, but that we aren't, right? We're choosing to do regenerative life support and regenerative power to enable the longer stays. So I think things like regenerative life support will allow us, right, to maybe not even let the atmosphere go stale, for example, in Gateway. We'll keep it on, right, let those systems operate all the time so that the system is ready for the crew to arrive and allows perhaps science that requires those atmospheric conditions to continue. Could present some really interesting situations, right? Even in human spaceflight so far, we've seen interesting microbiology issues with some of our water cleaning systems and filters, even on space station, right? So it's a challenge to keep the water systems clean. And so I imagine we'll find a lot, we'll learn a lot. We'll learn a lot about what it's like to keep a clean house on Gateway for extended periods of time.
Hi, I'm Ana Diaz-Artiles, one of the chairs of the program. Thank you so much for your talk. It was really, really great. And at some point you mentioned the CST at the Boeing capsule up there. So I was wondering if you can give us a little bit of a summary of what's going on. We see a lot of things in the press, which is probably not true. Astronauts stranded in the station.
Yeah, that part I have to say no. I have to say no to that.
Which is definitely not true.
Yeah.
So we would love to hear. I would love to hear your whatever you can give us about the situation.
Well, I think I can give you a high level. I can kind of help parse for you a little bit about what in the press is true versus what is maybe not true, right? I mean, the spacecraft is a test spacecraft. We knew it had some features that we had seen in OFT-2, which was the second flight test, but had corrected a lot of issues we had seen in OFT-1. Spent a lot of time going through the software, testing, made some really significant improvements. But the vehicle was a very robust vehicle, was able to make it through its initial flight tests. So what we saw with this last flight was we were having some challenges with some helium leaks on the vehicle. It was leaking at the pad to a lesser extent than it is now. So we've got some challenges with helium leaks that we would like to know are not going to get so bad on reentry that we would have an issue, right? I mean, you got a limited amount of helium on the spacecraft. Right now, they're nowhere close to levels that would be a problem, but we want to be sure before we return the crew. And we've got some issues with some funny engine behavior. Again, the vehicle was able to dock with space station, but we want to understand it before I return the crew, because I really don't need to immediately return the crew. If I had to return the crew, I would have no qualms whatsoever about them getting in Starliner and coming back. But because I've got them on space station, I'm not rushed to get them off space station, really. I can make them work while they're on space station. That makes the Expedition 71 guys happy, because now Sunny and Butch are having to do work. Nobody minds being asked to stay in space a little longer, generally. So it's kind of a win-win. It allows us to just take our time, not rush, understand what's going on with the thrusters and the helium system. So that part, what you read in the press, is true. They're not stranded, right? I mean, okay, whatever. I mean, we could come back in Starliner. But really, the key is that it's a test flight. So for me, there's no reason to rush, and the space station is not pushing them off. So we'll stay a few more weeks until we really have a good feel for kind of what's going on. They're doing a lot of work. Boeing is doing a lot of work at their factory in Florida to kind of understand the helium leaks. They're doing some really good work out at White Sands to understand what's going on with the engines, and I hope we'll know a lot more next week, is what I would say, and maybe it's a couple weeks after that before we come back.
Hi, my name is Prathamesh. I'm from India. Given that RS-25 engines has been utilizing from Space Shuttle and now at SLS, why did NASA continue to utilize it further? And what was the reason behind choosing RS-25? And is there any scope of new engine development for upcoming missions?
Have you seen an RS-25? Yeah. They're big. That's why we use them. They're big. They go with big rockets. Big rocket engines. They go with big rockets. They were sitting around. Why not use them, right? I mean, literally, they were sitting in warehouses, in drums, right, not being used. They were built to be used. They weren't going to be used on a space shuttle anymore. So I think actually using them is very efficient. It has some downsides to it, so I'm not trying to be totally facetious, but they are an amazing engine, by the way, from a performance perspective. So great engine, sitting around, why not, right? Now, what do I do when I run out of them, right? That's the key. And so the program's committed, right, to, I won't say restarting an RS-25, because it's not exactly, you know, it doesn't need to be the same engine that it was on shuttle. It's got a totally different set of requirements, particularly in terms of reuse and total runtime and all those other things, right? Well, the reuse and the runtime and all that, that's what drove a lot of the cost of that engine, right? Was to be able to reuse it, relight it, use it for 100 missions, right? So working with the engine contractors to kind of streamline some of that out and make it simpler and replace a lot of parts with additive manufactured parts, which were not the thing you could do in 1980, right? 1970, some of these engines, right? So I think streamlining that and adding modern technology, hoping to have an engine, right, to develop an engine that is of similar performance at a lot less cost. So really the answer is why not, right? By the way, Orion uses the OHMS engine. That engine is almost as old as I am. And it operates awesome. And it sat in barrels, right, out at White Sands Test Facility. So it is a great engine. And we had a bunch of them sitting around in barrels. So we said to the Europeans, would you like our engine? And they're like, sure, why not? Now we'll start with the line to build new ones. I think after 9, I think we had 9 of them or something that we could use. We take them out of storage, we recertify them in our labs at Johnson Space Center. We vibe them and change out a bunch of seals and work with our friends at White Sands to retest them and hot fire them to make sure they're going to operate good. And they operated great, operated flawlessly on Artemis 1. So we'll be using old shuttle OHMS engines for a couple flights while they restart the contracts to build new ones. Again, incorporating the new performance requirements to try to make a simpler engine than the OHMS engine, which doesn't have the same reusability requirements, and it incorporates all the modern additive manufacturing techniques that are so common in engines now that weren't common then. It's working to bring the price down.
Okay. In your opinion, what are the main technological gaps we have to solve before launching a crewed mission to Mars? What are the key elements the Lunar Gateway has to demonstrate before such a mission? And do you think the Gateway will operate as an analog spacecraft to a Mars transfer vehicle?
Yeah, we talked about a few of them. You know, the transportation one, to me, is one that's kind of optional to solve, right? I mean, that would really not be super awesome to spend 6 months going to Mars, 18 months at Mars, and 6 months coming back from Mars, right? You're approaching a 2.5, 3-year mission, but we could do it. I don't know that it would be any fun, but you could do it. You'd have some medical issues you'd probably have to deal with. We'd have to be really careful about the radiation and some of the other things. Things that are not negotiable, right, is how to enter the Martian atmosphere, like we mentioned. So re-entry is going to be a big challenge. And I think probably ultimately weather is going to be a huge challenge for us on Mars. So even no matter how good we get at operating on the moon, I think this dealing with weather is going to be a huge challenge. You know, latent time delay, it's certainly an issue, but we operate, you know, JPL operates that way all the time. I think we would learn kind of to deal with some of those things. But I think the reentry physics piece of it and safely entering in through that thin atmosphere with a lot of mass, as well as some of the challenges with weather are going to be some of the big ones from an engineering perspective.
Hello, I'm Nadine. I'm from the Netherlands and I study robotics and space engineering. I think you have a very interesting career and I find very interesting to hear about all the projects that you've worked on. But I'm wondering, what were the greatest challenges you've experienced so far to get to where you are now? And what are things you wish you knew before that you know now?
Oh, gosh. So many things. How long are we staying here about the things that we wish we knew? So let's see. I think probably, I would say that the things that looking back now as a senior, but as a chief engineer, as a senior engineer, right, and now as a manager of engineers, you might be surprised or maybe not. I've watched some of the topics you guys have talked about, so might not be surprised that my biggest challenges or my things that keep me awake at night are not technical for the most part, right? It's people. If I could do this without people, that would be so awesome. But except the astronauts, I got to have them. But the rest of the people could go. Managing people and managing facilities is tough. Those are some of the biggest challenges. I think we as an agency, we with our international partners, our commercial partners, I think honestly, when it comes down to technical challenges, we may differ in approaches. We may, but ultimately, we all respect each other and appreciate the engineering piece of it, right? The challenge, right? You got a good problem. Everybody wants to go help solve that problem. And that's when we tend to do some of our really best work collaboratively. But the challenges with communication, challenges with decision making, because engineers love data, right? So getting engineers to decide anything is a challenge. And so I think for me, as somebody inside NASA and having come up in technical leadership within NASA, I was surprised, kind of looking back on my career, how much of it really didn't have to do with technical, that it had to do with the ability to organize people, get them to make a decision, get them to communicate for them, help decision makers make decisions with a reasonable decision velocity, balancing, you're never going to have all the data, and I need you to make a decision, right? And then balancing that and trying to articulate what we think the risk is. And that is a skill that is not very common in engineers. So when I talk to people that want to work at NASA, I talk to them about, yeah, you need to take more software because like I learned Fortran 77 and that's not very useful. And software is ubiquitous, right? Software is everywhere in our spacecraft now. So there's very practical sort of technical things I tell my young engineers and people in school. But the things that really are going to ultimately get us where we need to be is taking those super smart people and partnering them with people that can integrate them, help them make decisions, people that can help contracts, help hire the right people, help tell their story from a communication perspective, right? It's those pieces are what kind of make the difference ultimately in how the programs operate, which was surprising to me.
Hi, Iqbal here from the United Kingdom. Thank you so much for coming here. I think you've actually kind of answered one of my questions already in a roundabout way. So I'll keep it a bit easier, if I may. I was going to ask for an example where you might have had to resolve something with other departments or somewhere around there too, and what have you done? I think you kind of answered that quite nicely. The other one was, yeah, one of the most funniest questions that you've been asked about space or about NASA? By people. Yeah.
Well, my family wants to know where the aliens are. I grew up in Indiana, so it's like, when I go back to the Midwest in the United States, I have to answer like why I don't know where the aliens are. It's sort of the standard repertoire of, kind of how do you go to the bathroom in space? What do you eat in space? Those are all kind of the standard sort of bizarre questions. Nobody asks funny engineering questions. They're all really reasonable questions, I think. So I don't have any good, strange engineering questions.
So please a round of applause for Julie. Here's a little token of appreciation.
This was an incredible lecture and perfect segue for the ones that are coming up next week, because we have next week the Lunar Landers commercial panel. And then after that, we have a panel on Artemis. So your presentation was a great overview for what's coming. So thank you, everybody. We're going to have a small reception right next door. You can continue to ask Julie more questions. Have a great evening.